Hi, everyone. Welcome to the second part of Lecture 18, Searching for Life in the Solar System. In this lecture segment, I'm going to talk about where in the solar system we might look for life and give an overview of some of the habitable locations that we may go into more detail, that we will go into more detail in the rest of the semester. So here's an image of the major planets in our solar system. There are these four inner planets over here, Mercury, Venus, Earth, and Mars. And then there are four gas giants, Jupiter, Saturn, Uranus, and Neptune. Where among these planets or the surrounding environs could we find life? So in the last lecture segment, I talked about how we want to start out looking for life by trying to find stuff that's similar to what we know on Earth. And generally that means we want to find things that are on surfaces like those of a planet. And we think that liquid water is important. But of course, we want to keep an open mind and not try to miss anything just because it doesn't fit into our potentially narrow-minded view of what life might look like elsewhere in the universe. So where are the surfaces in the solar system, the places where we think that life might arise? These are places where life could exist that's similar to the life here on Earth. So if I just go through all of the rocky, potentially habitable surfaces in the solar system, you start off with the four inner rocky planets, Mercury, Venus, Earth, and Mars. Of course, one of these planets we do know has much life on it. Earth is a particularly nice world, I hear. And then you have these other three planets, which are not nearly as pleasant to live on right now. We also have the possibility that there are other surfaces in the solar system, like moons and smaller planets, that could be places where life could arise. And interestingly, there's somewhat of an overlap between the sizes of moons and the sizes of planets. So these are the small bodies in the solar system given an order of size, so showing everything smaller than the Earth. You have Earth and Venus, which are both planets, and you have Mars, the next largest object. And then the next largest object is not another planet, but is Ganymede, which is a moon of Jupiter. Then you have Titan, a moon of Saturn, and then the next largest planet, Mercury. And then you have several more moons, Callisto, Io, our moon, the Earth's moon, Europa, Triton, and then finally Pluto, which is what we now classify as a minor planet or a dwarf planet out in the far reaches of our solar system. So there's actually quite a bit of potentially habitable real estate on these moons, even though they're not planets in the traditional sense that they orbit around the sun. They orbit around some other planet. We know that Earth's moon is a relatively large one, but there's a good number of other large moons elsewhere, and most of those happen to orbit the gas giants in our outer solar system. In particular, Jupiter and Saturn have lots and lots of moons, and some of the largest ones in our solar system. Here's an image of some of the large moons of Jupiter orbiting them. So the other place that there are surfaces in the solar system are what we call the minor planets. So, or the dwarf planets. These are planets that are big enough to essentially be shaped into something that's resembling round, although some of them are spinning so fast they get distorted, like Haumea. And potentially these have surfaces and could have, water and life on them as well. These all form among other groups of smaller bodies in our solar system. So in the middle of our solar system, lying roughly between the orbits of Mars and Jupiter, is what we call the asteroid belt, which is a large number of small bodies that are all orbiting kind of in a swarm. The biggest of these is Ceres, which was on this previous slide here. Ceres, the largest asteroid in the asteroid belt. And then there's a large number of distant objects in what's called the Kuiper belt and the Oort cloud. And some of the other minor planets, dwarf planets that we know about, like Eris, Pluto, Haumea, Makemake, these are all in the Kuiper belt. There's also, we believe, a large clump of objects orbiting much further away because we see them occasionally fall towards the sun, but they're so far away at their current distance that they're essentially invisible to us. So there may be large objects out here in what's called the Oort cloud, very, very far from the sun, but we haven't discovered any of them orbiting way out there yet. Only when they come closer to us can we start to see them. So one question was, where are the surfaces on which life could live? The other important question that we think is going to help us decide where the most likely place to find life in the solar system is where's the water? So we know that here on Earth, there's lots of water. We can go to the oceans and see these gigantic reservoirs of water. And we know that it's important to life because we have to drink it every day to survive. So, where should the water be in the solar system? I want you to recall all the way back to when we were talking about how planetary systems form, and recall that based on our observations of our own solar system and of others, we've seen that planets tend to orbit in ways that suggest that they formed in disks, and we have this thin disk of material that's all clumping together and building planets. And also remember that not all of the materials in the disk are in gas form in the protoplanetary disk. When you're close to the star, the disk is warm enough that only rocky materials like iron and silicon stay solid. But if you go far enough away from the star, you can get to a cool enough region of the disk so that water can remain solid as well. And because solids tend to clump together, and stick together more easily than gases. Here's an example of this where Will Ferrell is throwing a clump of solid water and it's holding together, but this clump of gaseous water is essentially dispersing very quickly. We think that wherever water can be solid in the solar system is where much of it's going to end up because it'll end up clumping together. So even though in hot regions of the disk, close to the star, only rocky materials will stick together. Beyond a particular point, which we call a snow line, this region here, you will actually get ice that's clumping together as well. And that's where we expect that most of the water in our solar system should be. And indeed, it turns out that that's the case. This is a chart showing the amount of water in many of the bodies of our solar system. Interestingly, despite Earth feeling like a really wet planet, it actually has a relatively small amount of water. There are several moons, 6 moons in the outer solar system, including Pluto, which is a dwarf planet, that have more water on or in them than the Earth does, despite the Earth being much larger overall. So all of these images are sized to scale. And the reason is that essentially the water was in solid state out there, so it was able to clump together and to form these big water rich moons and dwarf planets. So, where's the water now? Because of that exact fact, the inner rocky planets tend to have relatively little water. Earth has lots of water today, but the rest of them don't. Others may have gotten similar amounts of water in the past, but since then it's long gone. And in fact, we have pretty good evidence that there is water on there was water on Mars in the past, even though there's not much of it in liquid form around today. So the moons and the minor planets, especially the ones in the outer solar system, have large water reservoirs. But is it necessarily liquid water? Because these are really far away from the star, that's why the water was able to clump together, was because it was able to form into ice. But if it's in ice, it doesn't really do life much good because you can't have the interesting chemistry needed for life in a solid like ice. So you need it to be in liquid form, which is why everything works so nicely here on Earth, because there's both a good amount of water and it's warm enough here to keep it in liquid. So is there any other way that we can get liquid water far out in the solar system? And it turns out there's another way to heat up ice and to essentially make it into a liquid, and that is by deforming it. It turns out that when you have some material and you deform it, that heats it up. So this is a video that's going to show this fellow taking a hammer and hitting silly putty with it. And he has attached a temperature sensor into the silly putty so he can monitor how the temperature of that silly putty changes when he deforms it with that hammer. So I'm going to play this video. So he's going to take this hammer, he's going to whack the silly putty, and now we're going to look at this graph over here, which is showing the temperature of the silly putty on the y-axis versus time on the x-axis. And you can see that there's this sharp rise in the temperature of the silly putty as he hit it, and essentially smoothed out at the top as that heat, that energy from the deformation essentially rippled all the way through the silly putty. So hitting something, squeezing it, stretching it, deforming it can heat it up. Here's another example. So this woman is going to take a piece of metal and she's going to stretch it back and forth with her hands while wearing gloves. And we're going to look at it in the infrared, which essentially shows us how much heat there is coming off of the object. When you start this video, you can see that I'm going to show it again here. When you start this video, you can see that the metal is dark, which means it's cold in the infrared. But bends it as she bends it forward and backwards, you can see that the metal starts to become brighter. It starts to heat up. This is the deformation of that metal causing it to warm up. And you can see it in this infrared image here. So why am I talking about deforming things? It turns out that you can actually deform planets or moons based on gravitational forces. This is called tidal forces. When you have a body orbiting close to another body, it essentially stretches them out just a little bit. And as the other body goes around, it stretches them in different directions. And it's essentially continuously deforming that material. It turns out that for some of the moons in the outer solar system, and the most dramatic examples of these are the moons of Jupiter and Saturn because they're orbiting massive bodies with a lot of gravity, that deformation is enough to warm up the ice in the center of these moons and essentially form large liquid oceans underneath the frozen surfaces. And occasionally you can get the water rushing to the surface and spraying out in geysers. So the fact that you now have warm liquid water on these two moons has made them prominent examples of places where we think life may exist in the outer solar system, even though without the benefit of these tides, it would be too cold for the life to exist because the water would be in ice form.